Hello, welcome to short lectures in physics. Topic for discussion is reflection and refraction on the basis of wave theory of light. Reflection of light principles can be explained through Huygens wave theory. Consider a smooth reflecting surface as shown in the slide. The surface is Mn onto which a set of rays like OP and QR are incident at an angle of incidence I as shown in the slide. The ray from O incidents at a point P while the ray at Q touches the surface at point R. Both the angle of incidence is I. The ray from O that was incident at P gets reflected as a ray PU. Let PS be the incident plane wave front. According to Huygens principle, every point on the primary wavefront like PS can act as a source for generating secondary wavelets. So if we consider the secondary wavelets from different points on the plane wavefront PS, by the time the ray from O reaches P, the ray from Q will be at S in the same time interval. Let the secondary wavelet from S takes t seconds to reach the reflecting surface at the point R, so that distance SR is equal to v into t, where v is the velocity of the light. In the same time interval t, the secondary wavelet from P will also travel through bt distance as a reflected ray above the reflecting surface Mn. Then, with P as center and Vt as radius, now draw an arc such that Pt is equal to Vt. Now from point R, draw a plane tangent such that it touches the above arc at point T as shown. The plane indicated by the points R, T, U will be the reflected wavefront of the incident wavefront Ps after a time interval of t seconds. The reflected wavefront moves in the direction of reflected rays Ptu and Ry. Now, following the simple geometry principles, it can be easily shown that angle SPR is equal to the angle of incidence as shown at the point P, and angle TRP is equal to angle of reflection R. From triangles PSR and PTR, it can be seen that angle S and angle T are right angled, that is 90 degrees. The side PR is same for both triangles. Also, the sides SR and PT are same and is equal to VT. Thus, both the triangles will be congruent. Hence, it can be understood that angle SPR is equal to angle TRP, or angle I is equal to angle R. That is, angle of incidence is equal to angle of reflection, which proves the first law of reflection. Hence, we proved the first law of reflection. Further, the incident ray, the reflected ray, and the normals at different points all lie in the same plane, that is perpendicular to the plane of the slide, thus proving the second law of reflection. Hence, we prove the laws of reflection based on the Huygens wave theory of light. Now let us go to refraction. Huygens wave theory can also be used to prove the laws of refraction. Now consider again a parallel beam of light with rays like AB and EG falling at an angle of incidence I at the surface Mn that separates two mediums. One is rarer medium above the Mn and a denser medium below the surface Mn. And these rays are getting refracted at an angle of refraction R as shown. The BF is the incident wave plane wavefront to which all the incident rays are perpendicular as shown. The refractive index of rarer medium be mu1 and the denser medium be mu2 as shown. Now, by the time the ray from point A reaches the point B at the boundary surface separating the two both media, the ray from point E will be at F. According to Huygens wave theory, every point on the primary incident wavefront can act as a source of secondary wavelets. Let the secondary wavelet from point F takes t seconds to reach the reflecting surface at point G. Thus, Fg is equal to V1t, where V1 is the velocity of light in the rarer medium. In the same time t, the refracted beam from point B will also travel through V2t distance in the rarer medium, where V2 is the velocity of light in the denser medium. So in the rarer medium, it traveled through V1g, that is Fg distance, whereas in the denser medium, the ray BC is equal to V2t in the same time interval t. Now, with B as center and V2t as radius, draw an arc such that BD is equal to V2t. Now, from point G, draw a plane tangent such that it touches the above arc at the point D. Now, the line joining the points G to D will be the new refracted wavefront of incident wavefront BF after a time interval of t seconds. That means the plane wavefront BF got moved through some distance in the denser medium, and the new refracted wavefront will be GD after a time interval of t seconds. The refracted wavefront moves in the direction of refracted rays like BC and GH. These rays will be parallel to each other and perpendicular to the new wavefront GD. Now again, following the simple geometry principles, it can be easily shown that angle FBG is equal to angle of incidence I, and angle BGD is equal to the angle of refraction R. Now if we see the two triangles, triangle BFG and the triangle BGD, we can see that angle F is equal to angle D is equal to right angle, that is 90 degrees. The side BG is the same, common, and sides FG is equal to V1t and side BD is equal to V2t. Now, from one triangle you can see sin I is equal to V1t by BG, and from the other triangle sin R is equal to V2t by BG. Now, take the ratio sin I by sin R, that will become V1 by V2, which is nothing but the refractive index of medium 2 with reference to the medium 1. That is refractive index of denser medium with reference to rarer medium in the present case. This proves the Snell's law of refraction, the first law of refraction. Further, the incident plane wavefront BF, the refracted wavefront GD, and the refracting surface MN all are perpendicular to the plane of the slide as shown in the figure, as the incident rays, refracted rays are perpendicular to the respective plane wavefronts. Both rays as well as the normal all lie in the same plane, thus proving the second law of refraction. Hence, the Huygens wave theory can be used to prove the laws of refraction. Now let us see the effect of diffraction on frequency and wavelength. Consider a source of light in one medium with the refractive index mu1, and it is being observed by a person standing in the other medium of refractive index mu2, and let both the source and the observer are at rest so that there is no relative motion. Thus, the time taken by the light to travel from source to observer through both media remains same. Let v1 and v2 be the velocities of light in the medium 1 and medium 2 respectively. Consider the source is emitting two successive wavefronts, plane wavefronts, with a time period of t seconds, so that they reach the observer in the same time gap of t seconds after getting refracted at the boundary. Source being same, frequency n will be same for both wavefronts, and it is given by 1 by t per second, that is the unit of the frequency. Hence, source being same, the frequency will be same. It is not affected because of the refraction. As velocity of light is different in both media, let the respective wavelengths of the two lengths be lambda 1 and lambda 2 for the both mediums. Since 1 mu 2, that is refractive index of 2 with reference to 1, is mu 2 by mu 1, that is equal to v1 by v2, that is equal to n lambda 1 by n lambda 2, because v is equal to n lambda. Hence, the refractive index of the medium is equal to lambda 1 by lambda 2. Thus, wavelength of a light in a medium is directly proportional to speed of light in that medium and is inversely proportional to the refractive index of the medium mu through which it travels. In other words, if a smaller wavelength of light is traveling through a medium, then the refractive index of that medium will be greater, and the reverse is also true. So this is how the Huygens wave theory of light can be used to explain the principles of reflection, refraction, and its effect on the frequency and wavelength of light sources. Hope this is useful in understanding the Huygens wave theory concepts. See you in the next lecture with some other interesting topic. Bye.